In this video, we're going to learn how to graph polar equations by plotting points. And in this lesson, we're going to look at the graphs of roses, lemniscates, and spirals. We'll start with this left graph, which is r is equal to 4 cosine of 2 theta. Now, first we're going to test for symmetry to see where to plot our points. So r is equal to 4 times cosine of 2 times negative theta, which would be negative 2 theta. So 4 cosine of negative 2 theta. And since it's an even function, we can get rid of that negative and we have an equivalent equation. So it is symmetric with respect to the polar axis. So it's symmetric with respect to that positive x-axis. Now we'll test for symmetry with respect to the line pi over 2 by plugging in pi minus theta for theta. So r will equal 4 times cosine of 2 times pi minus theta. I'll distribute that 2. So 4 cosine of 2 pi minus theta, and the period of cosine is 2 pi, so I can actually subtract 2 pi from the inside, and it should be an equivalent expression. So I get 4 cosine of negative theta, which I can also use that even property to get rid of the negative to get 4 cosine of theta. So it's also symmetric with respect the line, with respect to the line, theta is equal to pi over 2, which means if it's symmetric to both of these, it's going to be symmetric with respect to the origin, or the pole, rather, since I'm in polar coordinates. Now, I know this, you really only need coordinates from 0 to pi so I can reflect everything properly. And since I also know it's symmetric about these two, I can also just reflect across to get those points, and so on and so forth. But one thing I like to do whenever I start to get these like 2 thetas on the inside, I'll actually just plot angles within the period of that trig function. Now, the period of a trig function is found by doing 2 pi over the coefficient in front of theta, which is like omega. So 2 over 2, 2 pi over 2 would be pi. So I'm actually just going to plot points from 0 all the way to pi. It's usually the safest bet when you're dealing with these types of functions. But just know that we'll probably start to see repeated values, or when we start reflecting them, we'll see how they'll land on top of each other. But hopefully after one period, it just repeats its values again, all the way up to 2 pi. So between 0 and pi, we have pi over 2. And then the unit circle angles between those are pi over 6, pi over 4, pi over 3, then 2 pi over 3 after pi over 2, 3 pi over 4, and 5 pi over 6. So if I were to plug in 0, that'd be 4 cosine of 0, which is 4 times 1, so 4. And then I have 4 times cosine of pi over 6, which will be 4 times cosine of 2 times pi over 6, which is pi over 3. So 4 times a half, which will give me 2. And then pi over 4 would be now cosine of 2 times pi over 4, which is pi over 2, which is going to give me cosine of pi over 2, which is 0. So 4 times 0 is 0. And then 4 times cosine of 2 times pi over 3, which would be, 2 times pi over 3, which would be 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. So 4 times negative 1/2 is negative 2. 2 times pi over 2 is pi, so 4 times cosine of pi, so it's 4 times negative 1, so negative 4. And then 2 times 2 pi over 3 is 4 pi over 3, which is negative 1/2 for cosine. So 4 times negative 1/2 would be negative 2. Plug in 3 pi over 4. And by the way, I'm using unit circle values, but if you're nervous, just plug it into your calculator, and you'll get the same values. 2 times 3 pi over 4 is 3 pi over 2, which is 0 for cosine. So 4 times 0 is 0. And then 2 times 5 pi over 6 is 5 pi over 3, which is a positive 1/2 for cosine. So 4 times 1/2 is 2. Then 2 times pi is 2 pi, which will be cosine of 2 pi, which is 0. Oh, sorry, which is 1. So 4 times 1 is 4. And now I have plenty of points to start graphing this. So I'm going to start with 0, 4. So 1, 2, 3, 4. Then pi over 6. This is pi over 4. I'll just label these real quick. Then pi over 2 up here. Then 2 pi over 3, 3 pi over 4, and 5 pi over 6. And then pi. At pi over 6, it's 2. At pi over 4, it's the 0. And then at pi over 3, it'll be negative 2, meaning it actually goes through this point over here for pi over 3, because negative 2, so if that's pi over 3, negative 2 will go in that direction. And then at pi over 2, it's negative 4, so instead of going up to 4 here, I actually go down to 4 on the other side. And then at 2 pi over 3, it's a negative 2, so instead of going to 2 this way, I would actually go 2 in the other direction. And then for 3 pi over 4, it's back at 0. And then 5 pi over 6 is 2. And then at pi, it's 4, positive 4. So I'm not done graphing, but I'm going to plot everything I have so far. So if I go from this point to that point, then went to 0, and then went to this negative 2. Went up to this point, then I went through this point. These are all the negative angles I'm on right now. So right now I'm at pi over 2, negative 4. Now I'm going to 2 pi over 3, negative 2. Then back through the center again. And then through this point, and then that point. And I still have more points to get. I can get by reflecting across the origin and everywhere. But if I continue the same pattern, it goes 4, 2, 0, negative 2, negative 4, negative 2, 0, 2, 4. Following this would be 2, 2, and then 0, then negative 2, then negative 4, then negative 2, then 0, then 2, then 4. And it follows that same pattern forever. So from here, the next angle at 7 pi over 6 should be 2, following the same pattern. You'll see that's reflected across the polar axis. Or you can think about the origin as well, straight across. Then it would be 0 at 5 pi over 4. And then it would be negative 2 at 4 pi over 3. So straight across, negative 2. So again, following this curve, it actually goes through this point, through the origin, then back up through this point. And then from negative 2, we go to negative 4 at 3 pi over 2. And then to negative 2 at 5 pi over 3. So this point, but straight across to negative 2. Then back to 0 at 7 pi over 4. Oop, I had that point on the wrong spot. So you'll see here if I follow through these points, goes up, back here, back to 0. And then at the next angle, 11 pi over 6, we go to 2. Then at 2 pi would be back at 4. So 11 pi over 6 here, be at 2. And then back to 4. me call this graph a rows. You'll see here, I kind of cover up some of my space to write it. But on the right, on the left over there, that would be a rows. If it's ever an even number inside, it's a rows with 4 end petals, so 4 times or double that number. So here we have a rows with 4 petals. And if it's ever an odd number on the inside, that's a rows with the exact same number of petals. So with the same odd number of petals, so 2n plus 1. And as long as you use that period, you'll always find all of the petals on your graph. Yeah, you'll also see here it's always multiples of 4 or odd numbers. So numbers like 2 and 6 and 10 that don't fall into those two categories actually don't have those simple rows graphs. Actually, you do have to do something more clever. And I'll leave it up to you to maybe figure that out. But let's look at this next example where we have r squared is equal to 4 sine of 2 theta. Now we'll test for symmetry, but we only have to test for symmetry about the origin. Since r is squared, I can already tell it's going to be symmetric with respect to the origin. So I'll square the r, and I'll also have r squared is equal to 4 sine of 2 theta. So it's symmetric with respect to the pole, the origin. So I just need to get points from 0 to pi, but what's really nice is sine of 2 pi happens to be negative from pi over 2 to pi. And since r squared can't equal a negative number, I actually just need points from 0 to pi over 2. And I'll pick up a spot in the middle, so like pi over 4. And I'll use pi over 6 and pi over 3 for my other points. Now doing this, plugging in 0 for sine, this will give me r squared is equal to 4 times 0, which is 0. So that means that r is just equal to 0. If I plug in pi over 6, that's sine of pi over 3, which is the square root of 3 over 2. So 4 times the square root of 3 over 2 means r squared is equal to 2 square roots of 3, which when you take its square roots, you get plus or minus 1.9. Then when you plug in pi over 4, it's the same thing as sine of pi over 2, which is 1. So that's just r squared is equal to 4, which when you take its square root is plus or minus 2. And then plug in pi over 3, you get 2 pi over 3, which is square root 3 over 2, giving me r squared is equal to 2 square roots of 3, which is, again, plus or minus 1.9. And then pi over 2 gives me 2 times pi over 2, which is pi. Sine of pi is 0, so that's just r squared is equal to 0, which is 0. And it's really nice with this plus or minus because it actually takes care of that symmetry with the pole. So when I go to 0, I'll just have a point at 0 radius. At pi over 6, I'll have a point at 1.9, which is just below that radius of 2. And it'll also be directly across as well with the negative radius. At pi over 4, I'll have a radius of 2 and negative 2, so straight across. At pi over 3, I'll have a radius of positive 1.9, so just below and straight across. And then I'm back to 0 at pi over 2. If I were to try, for example, 2 pi over 3, that would give me 4 pi over 3, which is negative square root 3 over 2, and r squared cannot equal negative 2 square roots of 3, because that leads to an imaginary solution. So if I go to graph this, it actually creates like an infinity loop, what they call a lemniscate as well. It's another word for an infinite loop. And those are just usually if you have r squared and then some other number that you would take the square root of to see how far it goes out. They call this a lemniscate. And lastly, we have spirals. These are usually not symmetric about anything, and they don't use a trig function. So there's no periodic values. This just gets bigger over time. So it's not going to be symmetric about any of these lines because it's just going to keep getting bigger in some way. So we're actually going to plug in quite a few points, which will be negative 3 pi over 2, negative pi. We're going to get a lot of points around the circle, just so you can get an idea of how this works. Oop, not 0, but negative pi over 4. Give another value. So negative pi over 4. Then 0. Then we'll do pi over 4. Pi over 2. And then we'll do pi, 3 pi over 2, and 2 pi. And we'll just plug all of these into the function. So meaning we'll use e to the negative 3 pi over 2 divided by 5. And that'll give us 0.39. And we'll continue to do this for all of these values. And just to save a little bit of time, I've calculated these ahead of time. So 0.53, 0.73, 0.85. And then e to the 0 is always going to be 1. And then 1.17, 1.37, 1.87, 2.57, and then 3.51. So I'm going to go ahead and start to plot these. Now these first ones are very small, so it's going to be hard to see. So I'm going to put 0, 1. And for these negative ones, for negative pi over 2, it'd be straight down. But about right here, negative pi would be about halfway. But you'll never quite get it down to 0 since e can't equal 0, that exponential. But very small, and it kind of continues to go down. But now after 0, we have pi over 4, which is about halfway here. It's 1.17, so just above that radius. Pi over 2 is 1.37, which is still about a little below halfway for pi over 2. For a pi, it gets a little bit bigger. We're at 1.87, still not quite the 2. Then at 3 pi over 2, it's 2.57, but between 2 and 3. Then at 2 pi, when we get back around to 0 again, it's 3.51, so 1, 2, 3 and a half. And when you see this graph, it'll keep spiraling down, but you won't quite see where it ends up. I'll put a little arrow there, but then it spirals outwards, and it just continues to grow. Kind of just infinitely bigger and bigger and bigger. And that's why we refer to these as spirals. So they'll keep spiraling down too. Now, if this was an exponential function, it might stop at 0. But since it's an exponential function, it keeps spiraling down there, and it keeps spiraling outside. So we refer to those as spirals. And that is how you graph polar equations, by plotting points.